suppose I have a data set, and that data set is a population of some sort of individuals, and I want to predict something based on that data set. Now let's say the instances in the data set are represented as pairs, so two attributes, each attribute is a real valued, it's a real number, and what I'm trying to do is I'm trying to sort of figure out, well, what is the dimensionality of the data? And if you just look at it on the surface, so I have two attributes, one is refu, another one is height, and on the surface it looks like two-dimensional data. All right, maybe then I get this data set and I plot the data and it looks like that, right? So I have height measured in inches, I have ref measured in centimeters, and the data looks pretty correlated, but it still looks two-dimensional to me. So it looks two-dimensional until my good friend from Africa comes along and says that that he speaks Swahili, and in Swahili, refu means height. Now that's an extreme example, but it is an example that would certainly fool me. If I got two-dimensional data like that, I would think that they are two different attributes. Now you look at this graph and you're going to tell me, wait. If they were the same thing, shouldn't you get the straight line? Yes, unless height was measured, say, in the UK, and refu was actually measured somewhere where they speak Swahili. And there they could easily measure the same object and get quite varying observations. Right? It happens all the time. Right? So this is a slightly contrived example, but let's look at another example. So let's say that I have, let's say that I'm observing a data set with the following 5 variables, right? So and it comes from different geographic areas over times, and what I'm measuring is the number of skidding accidents on the roads where car spins out of control, and the second attribute is how many burst water pipes I have per square kilometer of the population. X3, how many thousands I'm spending on snow plows. X4, how many school closures I had per unit of time in that particular region. X5 is how many patients I had with a heat stroke in that particular region. Right? So in this case, I have 5 variables. They're all numeric. So again, on the surface, the data looks like it is 5-dimensional. I have 5 numbers to represent each instance. But if you look at it closely enough, you'll realize, well, all of these are actually closely related to one specific measurement that I could do. Really, all of these are very strongly influenced by one factor, and that is the temperature. So if the temperature is below freezing, I'm going to have lots of skidding accidents on the road because there will be ice, water pipes will burst, I'm going to spend a lot of money cleaning up the roads of that snow and ice, so my snowplow expenditures is going to go up, schools are going to close, and people are not going to have heat strokes nearly as much as when the temperature is very hot. Right? So what you have is you have a data set which on the surface of it looks 5-dimensional, but there is really a single factor that could be responsible for all of those observations. So if you were doing your modeling right, if you're doing your machine learning right, you shouldn't be trying to model 5 attributes. You should really try to get at that. You should try to get at the factor that can explain everything else. That's going to be a lot more fruitful.